Okay, looks like we are ready to get going. Uh, Good afternoon, everyone. Thank you very much for joining the TRANS-IPIC Research Highlights webinar of May 2025. My name is Arslan Khan, and I am a postdoctoral research associate at the University of Illinois Urbana-Champaign, working with Professor Bassam and Raz. Today, I will be moderating this webinar session along with Chris. We have two very exciting presentations today for you, one from the University of Illinois Urbana-Champaign and one from the University of Texas at San Antonio. With the webinar, the formatting, if anybody has questions for our presenters, please feel free to add them into the Q&A at the bottom, and we will be monitoring that as the presentation go. We will save the questions for the end of each presentation, and the presenters can read the Q&A and answer any of the questions that the group has. With that, I think we can roll into the first presentation. So the first topic will be presented by Professor Khaled Al-Raiz and Hadil Hilali from the University of Illinois. Professor Khaled Al-Raiz is a professor of construction engineering and management and also associate head of the Department of Civil and Environmental Engineering at the University of Illinois. He has more than 30 years of professional experience in academia and the construction industry. Professor Al-Raiz has supervised the research work of 38 PhD students, including 28 former PhD students who are currently holding leadership positions in academia, industry, and government. The second presenter on this topic is Ms. Hadil Hilali. She is a PhD candidate and research assistant at the Department of Civil and Environmental Engineering at the University of Illinois. She has extensive experience in data analytics and machine learning. She is using her knowledge and experience in architecture, construction management, and machine learning to develop tools and optimization models that improve construction efficiency, performance, and economics. So, really excited to have this presentation.
Thank you very much, Arslan, for this kind introduction. Our presentation today will provide an update on our progress on an ongoing research project that is funded by TRANS-IPIC that focuses on optimizing the construction planning of precast concrete bridge projects in order to maximize durability, safety, and sustainability. I'd like to also acknowledge the other members of the research team, in addition to myself and Hadil, EJ Ignacio, who's co-PI on this project. In the next 20 minutes or so, I'm going to start with highlighting the need for this research, stating the problem that we're trying to address. This will be followed by the research objectives and tasks. And then I'm going to focus on two of these tasks. The first one is developing machine learning models to estimate or to accurately predict the construction cost of alternative construction methods for precast bridges. And the second one is an optimization model that seeks to optimize the construction planning decisions. And towards the end, I will end with expected research contributions and impact. As we are all familiar, the network of bridges and roads in the US have been aging. And in its latest report, ASCE reported that 42% of the US bridges are more than 50 years old. 23% of these 50 years old or more bridges are in poor conditions. And 7.5% of US bridges, old bridges, are structurally deficient. That's based on ASCE report. To address this aging and deteriorating bridges in the US, the federal government has invested $110 billion in additional funding to rehabilitate, to repair, and replace these aging bridges and roads. Of course, this major investment needs to be invested in a way that optimizes the the decisions so that we can accomplish multiple objectives, including maximum, of course, for transportation networks. The two main focus or the two main objectives is to maximize safety on the roadways and mobility as well. In terms of the infrastructure itself, we need to maximize its durability so it can last longer. And we need to maximize its sustainability to minimize its negative environmental impacts. And all of this needs to be done while we're trying to also control and minimize the construction cost. So as you can notice here, there are conflicting objectives that construction planners and decision makers in state DOTs need to consider and carefully analyze. So in our research project, we're focusing on two phases of the life cycle of a bridge construction project. The early design phase and some of the challenges that needs to be addressed, and also in the pre-construction phase. So I'm going to start first with the early design phase. And during this early design phase, bridge decision makers or decision makers in state DOTs, they need to identify what would be the construction method that's going to be used for their planned project. And there are alternative methods. The traditional one, of course, is the conventional cast in place, where all the activities are performed on site. That's the traditional way. However, its main limitation is that it takes longer. And of course, that causes significant delays because of the lane closures. It causes also higher risk of work zone related crashes. To overcome that and try to minimize the duration and its negative impact on traffic mobility and safety, there have been also the use of precast bridge elements that would be fabricated or precast off-site and then transported and installed on site to reduce the duration and the road closures. And that, of course, improves mobility and safety. Another variation of the precast bridge elements and sometimes use also cast in place is the third method that is shown here, which is the lateral slide, whereby the original bridge that needs to be replaced is kept in function or operational. And next to it, there is a site that is used to build a replacement bridge, as you can see here in this image. And during the construction of that replacement bridge, the original bridge is still functioning and providing service to the traffic. Once it is done, the original bridge, the old bridge, is demolished, and that new bridge is laterally slid, pushed with hydraulics to replace the old one. Of course, that reduces the overall lane closures and its associated traffic delays and risks or hazards on the road. Another variation of that is major sections of the bridge in the fourth method are cast off-site and transported using self-propelled modular transporters, for short SPMT. So during the early design phase, decision makers need to make a decision before even starting with the design process and developing detailed design for the bridge. They need to select which one of these methods would be used. A major challenge in that is how can we compare the costs of these alternatives? How can we compare their impact on the traffic delays and safety? And of course, because of the limited available data at that early design phase, the reliability and the accuracy of these cost estimates might not be as needed. And that's a main challenge that we're trying to address in this research project. Also, we're trying to predict what would be the condition of aging bridges over their life when we use these alternative methods. And this is also another challenge. And as I mentioned, how can we quantify the impact of these alternative construction methods on traffic mobility and safety? So this is the first main challenge that we are trying to address, as I mentioned, in the early design phase. In the pre-construction phase, we are faced with, after the completion of the detailed design, we need to try to make construction decisions that tries to minimize the project cost, minimize traffic delays, work zone crashes, and greenhouse gas emissions caused by the construction process. And there are several decisions that have an impact on all these important objectives. For example, for each and every activity, construction activity on the bridge project, we can have multiple, more than one possible crew uh, utilization or option. It could be different equipment. As you can see here, for example, we can have more than one possible crane that can be used. Each one of those might have a different cost and, of course, different duration and accordingly different impact on the project cost, traffic delays, work zone crashes, and greenhouse gas emissions. So which one should be selected? This is with regard to the selection of the construction crews or equipment. In addition to that, we can also utilize overtime. When we apply overtime, that would reduce the duration, reduce the traffic delays, associated traffic delays, and so on and so forth. So which crew and overtime should we use for each and every activity? Similarly, for the transportation of precast members from the prefabrication plant to the site, what trucks or which trucks from available options should be selected. And of course, those has an impact on the transportation cost as well as when it would be delivered on site and the storage on site. So again, to address these challenges, we have four main objectives. The first one is to develop machine learning models to accurately estimate the construction cost of bridges during the early design phase. The second, create novel machine learning models for predicting the condition of aging conventional and PC bridges. The third is optimizing or developing an optimization model that addresses the pre-construction phase challenge that we mentioned before. And objective number four is to implement a practical decision support tool that can be used by DOT decision makers so that they can compare the performance of alternative construction methods. Those four objectives are implemented using four tasks. Task number one is fully completed, and it resulted in two journal papers that are listed down here that have been published this year in January and in February. Task two and three are still ongoing. Task three is nearing completion. It's about 80 to 90%. And that's why I'm going to focus in my presentation today on objective one and three and their related tasks. So I'm going to start first with task one, developing the machine learning models to provide a reliable and accurate estimate of construction cost during the early design phase. This is developed in four main phases. The first one, as for all machine learning models, we need to collect a representative sample of data that can be used to train the machine learning models. This data is pre-processed in phase number two, and in phase number three, we develop these machine learning models using the training data. And in phase four, we evaluate the performance of these developed machine learning models using the testing data set. So I'm going to go quickly over these different phases. Phase number one, to collect a representative sample of different construction or alternative construction methods, we collected data from 29 US states for projects, bridge projects that were constructed between 1992 and 2024. Of course, the databases of these state DOTs have repair and replacement bridges. We focused on new construction or replacement bridges. For example, for each and every one of these state DOTs, it has its own, the data is sprinkled or distributed over different sources that we had to investigate and try to extract this data from. So for example, the Illinois Department of Transportation, the sources of data that we used to collect these required data for the prediction included the contract detail page, plans and provisions and documents, IDOT bridge information system, and the data that we were trying to collect, data that would be readily available during the early design phase, such as the project length, the bridge length and width, the number of spans, the maximum span length, the average daily traffic. So we had to extract this data for the available bridges. And the data set that we collected included 397 bridges or bridge projects from these 29 states. This data was then pre-processed so that we can classify and identify what are the predicted variable and the predictor variable. The predicted variable that we are trying to use here for the estimate is what is the unit cost for a bridge construction project in terms of dollar per square foot. And to provide that estimate or that prediction, the predictor variables that were reported in the literature to affect that unit cost of bridge included numerical and categorical variables, including, as I mentioned before, project length, bridge length and width, maximum span length. These are numerical variables that are continuous. Then we have categorical variables such as the number of lanes, for example, 2 lanes, 4 lanes, and so on and so forth, number of spans. And these data, after they have been categorized, we had to clean the collected data by identifying and excluding outliers to improve the accuracy of the prediction, and transforming the predictor variables to improve the performance of the machine learning model. And this data set was then split into a training data set, 80%, and testing data set of 20%. Then this training data set, the 80% of the 400, almost 400 bridges, were used to train different models. We used here 6 different algorithms, regression algorithms. 3 of them are linear regression algorithms, and 3 are non-linear to compare their performance. And as you can see here, in terms of the validation or performance evaluation, as I mentioned, we had a testing data set that included 80 bridges. This testing data set was never seen or used for training the models. So the models, the trained models, have never seen these bridges, which would be similar or representative of a future bridge that was not used for training these models. And as you can see here graphically, I'm showing the performance or the comparison between the true values that were reported for these projects and the predicted values by the models that we developed. And for 2 models here, the ordinary least square model, you can see here 80 bridges that were in the testing data set. And it shows here the orange curve shows the true cost in unit cost, dollar per square foot, and the dark blue represents the predicted one by the machine learning model that used OLS. And as you can see here, there is close, or they are very close and accurate for most of the projects. However, for the latter slide, the OLS model did not perform well. Another model that was developed, which is the extreme gradient boosting model, XGBoost, provided better performance for almost all of them, including the lateral slide and SPMT, as you can see here. So the 6 different models that I mentioned, their performance were evaluated using 4 main metrics. The mean absolute percentage error that represents how accurate it is. And as you can see here, the one that performed the best was the XGBoost that provided 13.9 MAPE, or mean absolute percentage error. And the other metrics also agree, including the mean absolute error, the median absolute error, and the root mean squared error. And the results of this was published, as I mentioned before, in a paper that was published in January of this year. We did another validation for the lasso regression model with a reduced number of variables, 8 variables, as you can see here, for precast bridge elements. And we compared our developed model, as you can see here, to 4 others that are reported in the literature. And our model, as you can see, was also outperforming the other models in terms of the mean absolute percentage error. So this is the first task. The second task, or the task number 3 within our project, as I mentioned, focused on developing a multi-objective optimization model to optimize construction decisions during the pre-construction phase. And the model was developed in 3 different stages: the model formulation, implementation, and performance evaluation. So for the model formulation, we had to identify the decision variables. I've highlighted them earlier. What type of crew should be selected for each and every activity, what overtime policy should be applied, transportation methods, which trucks should be used, delivery lead time, when it should be delivered. Is it on the day of installation, 1 day, 2 days, or 3 or 4 days, and requires storage on site? Another decision variable, the work zone speed that would be set up for this project, and it is within a range that sometimes are available for state DOTs. And based on this, we formulated the objective functions to maximize safety, maximize mobility, sustainability, and minimize construction cost. It is a multi-objective optimization model. And of course, we have constraints in terms of transportation based on the dimensions of the units that are represented here by orange that needs to be stored on the truck, as well as the dimensions of the truck, storage constraints on site in terms of the available storage space on site. And to give you an idea about the size of this problem, if we have a simple problem with 6 activities similar to this project, and each one of these activities can be performed using 6 different or alternative construction crews, that produces a possible combinations of all possible crews for the different activities of 6 to the power 6. In terms of transportation, if we have 100 PC elements in a project, and each one of them can be transported 4 different methods or alternative methods, that's 4 to the power 100. And the same applies for the delivery lead time. For the same 100 PC elements, if they can deliver it either 1 day before, 2, 3, or 4 days, 4 possible delivery lead times, that's 4 to the power 100. When you combine all of these combinations, you would end up with a very large space that includes the optimum solution, which of course cannot be enumerated or analyzed. So that highlights the need for an optimization model. So the model was implemented using multi-objective genetic algorithms, as you can see here, with the support of 4 additional modules. So we have a scheduling module that calculates the early start and finish schedule for each and every activity, and modifies that based on the work continuity, and then calculates the delivery date. The transportation module was designed so that also developed as part of this optimization model, and its main purpose is to try to calculate the minimum number of trips that would be needed to transport all the PC elements, and for each and every day, for each truck, which elements should be assigned. And just to simplify it, the algorithm seeks to try to minimize the number of trips. So for example, if we have here 4 units, PC elements that needs to be transported on day 6 of the project on truck number 1, the algorithm would first seek to combine or transport them all in a single trip. So for example, here, if we have 4 units as shown in this image, maybe if they can be stacked. If not, then the algorithm will try 2 trips instead. And if not, we'll explore 3 trips. And if not, we'll move on to 4 trips. So it tries to select the least number of trips that transports these elements. In terms of how it was applied, or the performance evaluation, we analyzed its performance using a construction project of a precast bridge in Illinois that had 120 feet long, 78 feet wide, and it has 3 spans, as you can see here, and it has 6 major activities: the excavation, the abutment, first, before the abutment, the cast in place piles, precast abutments east and west. We have precast or prefabricated piers. And then we have also prefabricated beams or precast beams. And we have the cast in place bridge deck. So for those ones, we need to provide what are the available crew formations or options that can be utilized. This is a sample of these for the installation of the precast piers or columns. As you can see here, we have 6 alternatives. Each one of them has its unique daily cost, daily output rate, equipment rated power, fuel consumption, and emissions based on the different cranes that can be used. Another example of the truck options, for example, here we can have 4 possible trucks with different areas that can accommodate the precast elements, weight capacity, cost per trip, fuel economy, and emissions, among others. And based on this, we performed the optimization and we identified from this large space that is 10 to the power 125. We narrowed it down using the multi-objective genetic algorithms to 355 non-dominated optimal trade-off solutions. That means each and every one of these provides a unique trade-off between the optimization objectives that we have. So for example, here, solution A that is represented here in the trade-off between the construction cost and the mobility score, where the mobility score represents the traffic vehicle delays in hours. The solution A that is represented here by this X provided the least cost for the project with a cost of approximately $1.8 million with a total vehicle delay of 64,000 hours of delay. On the other extreme, we have the least traffic delay of 49,000 hours, reduced it from 64 to 49,000 hours with an increase in cost of approximately $200,000. So this is for the state DOTs to try to evaluate the trade-offs and select the one that is best suited for this project. Similarly, we had trade-offs between safety and sustainability score, as you can see here. And these can be represented on these performance evaluation or parallel coordinates. So for example, here, solution A, which provides the least cost, it provides that least cost here. And this is its safety score and mobility score and sustainability score. Another optimal trade-off is between that provides the least traffic delay and work zone risks, again, is shown here. So those, again, can be used by state duties to identify the solution that they would select. So again, to wrap up, I know that we're running maybe maybe a few minutes late. The expected contributions of this research contributions is the development of original machine learning models for estimating the cost and durability. As we mentioned, 2 of them have already been published this year for the cost, an optimization model that supports decision makers during the pre-construction phase, and the decision support tool that can compare the performance of alternative construction methods. And that is expected to improve the prediction accuracy of cost and durability during the early design phase, maximize safety, durability, sustainability, mobility, and cost. And again, this is the list of publications that were generated from this TRANS-IPIC funded research. With that, I conclude, and I will be glad to answer any questions.
Okay, great. Thank you so much, Professor. We have been monitoring Q&A and we didn't see any questions. So participants, if anybody has questions for our presenters, please feel free to add them into the Q&A at the bottom. So maybe we can add 1 or 2 questions.
And if there are no questions now, please feel free to send me an email and I can follow up later on.
I don't see any question. If anyone has question, please feel free to add them into the Q&A. Okay, there is one question, Professor.
Yes.
Can you see it?
Yes. Yes, I'll read it out loud. For some precast concrete projects, the cost is much higher because the projects are one of a kind. Is there a way to consider this or any data on this? That's an excellent question, and we actually experienced that when we were collecting the data, especially for the lateral slide and the SPMT, because these are unique type of projects and unique transportation methods used to transport these larger sections. And in terms of their unit cost is much higher. So we try to collect as much data on these projects. And if you go back to the slide that showed the performance for the 80 bridges, the cost for these SPMT and lateral slide were much higher than the prefabricated elements. So the way that we can address it is to collect as much data and then use it to train the machine learning models so it would be able to predict that cost during the early design phase for a future project. And again, yeah, the question or Pinar is agreeing that the lateral slide and the SPMT were the ones that were causing or that have the much higher cost compared to the other types of construction methods.
Okay. Thank you for the question and thank you for the presentation, Professor.
My
I
pleasure.
think I think we are ready to move on the presentation from the research team at the University of Texas at San Antonio. So today we have Dr. Jiannan Cai and Juan Carlos Cruz. So a little introduction for Dr. Jiannan Cai. She's an assistant professor in the School of Civil and Environmental Engineering and Construction Management at the University of Texas. Dr. Kai's research interests include creating innovative sensing, artificial intelligence, and robotic methods to enhance construction automation and robotics, civil infrastructure and building management, and also community smartness and resilience. Her research has received fundings from various agencies, including National Science Foundation, National Institute of Standards and Technology, and University Transportation Centers. The other presenter is Juan Carlos Cruz. He is a master's student at the University of Texas studying advanced manufacturing and enterprise engineering. He is a research assistant in Dr. Kai's automated and intelligent construction lab, working on the robot system development and simulations. He has been awarded 2024 UTC Outstanding Student of the Year and 2024 Eisenhower Fellowship because of his excellence and contributions in this TRANS-IPIC funded project. Thank you very much for presenting to us. So let's hear from them.
Hello, thank you for the introduction. So today I would like to present our year one project with TRANS-IPIC, and it was completed by the end of last year. So I want to share what we have done and some of the results and findings and some of the challenges that we have found, and we can discuss some potential improvement that along the way. And I will be presenting the main, what we have done, the main content, and Juan could explain some technical details if there are any questions. So in this project, we develop a framework and a prototype for multi-robot and human coordinate construction inspection for precast bridge construction. So as many of us may know that the precast bridge component, such as the girders, decks, and columns, are very important. They facilitate the accelerated bridge construction, and they can offer improved construction quality because of the high quality control standards at the offset precast plant. In the offset precast plants, the components are usually need to go through rigorous dimensional and surface quality inspection. Then they will be transported to the job site for final assembly. However, the on-site quality inspection during the construction phase still largely relies on manual video inspection on limited samples. So it is time-consuming and subject to error, and also limited in coverage. To address this, our goal is to develop a robot assistant platform to improve the efficiency and coverage of data collection and inspection to enhance the QA/QC practice of on-site construction, bridge construction. And recently, there are some studies dedicated to developing approaches to automated inspection. And there are some approaches using robotic technologies, either from commercial solutions or from research development. I think the most widely used solution, or more of from a commercial available side, would be using UAV systems or drones to do the bridge inspection, where human operators can control the drone fly over the bridge to inspect the area. From academic and from research community, people also develop other robots platform for bridge inspection. For example, this study, they develop using UGV unmanned ground vehicle that carry different sensors, including 3D LiDAR, GPS for navigation, and they can collect point cloud data from bridges for future analysis and inspection. And in this study, they develop a method that to use a robotic arm to carry 3D LiDAR to scan precast concrete slab. And then by doing this, the robot will carry the inspection device or data collection device to automatically scan the entire component to improve the efficiency of data collection. And this last study I show is about using a wall climbing robot to inspect the concrete cracks. To despite these advantages, individual systems do have their own limitations and cannot satisfy all the requirements by themselves. And I use the most widely used two type of robot platform as an example. UAV, unmanned aerial vehicle drones, and UGV. For UAVs, they can scan or inspect the area rapidly, and they have a large spatial coverage. And they can also reach inaccessible areas from the air. However, they have limited payload and battery life. Also, it is difficult and even unsafe for ground activities that are very close to workers. I've talked with some of the construction companies. They use drones to inspect or monitor the construction site. And then what their feedback is that sometimes it's kind of distraction to the workers, or sometimes it's unsafe to the workers if the drone fly too close to the construction activities. On the other hand, UGV provide larger payloads with small sensors, and they have extended period of operation. Also, it has better access to the ground level workplaces. However, as an opposite way to the UAV, it has less field of view and a lower coverage speed. So what we think is that this two system is like a mutual complement to each other, and we want to leverage the advantages of both systems and develop a platform and see if it is it's possible to use UAV and UGV system to work together for the inspection. And in addition to that, there's another challenge is that current control interface for those robot systems usually require extensive human intervention. If you think about how now operator controlled UGV, UAV, it needs to it's like a step-by-step control. It control where it flies continuously. So it really require a lot of human intervention. It increase human mental load and of course the risk of error. So our objective is to develop a gaze-directed UAV-UGV coordination framework for on-site quality inspection of precast bridge construction. And we hope our system can leverage humans' domain knowledge and UAV's mobility as well as UGV's payload. So what that means is that this is an overview figure of our proposed framework, where the UAV will first fly to the area of interest and provide a global coverage for inspectors to quickly identify the components or the construction activities that they want to inspect. Then the UGV will navigate to that area of interest for closer inspection. At this point, the UGV could provide a closer view to that area of interest where the human operator could indicate which specific object or activity they want to inspect by using gaze instead of conventional physical devices to control the low-level movement of the robot. We hope such framework could reduce workers' mental load and also require less expertise on controlling the robots. To achieve this, we have 3 tasks. First, we need to develop a UAV-UGV coordinate navigation framework so that they can navigate automatically navigate to the same area, even if they are far away, they are not in close distance. And the second task is to develop a gaze-directed AI-powered human-robot interface so that the human can use their natural gaze movement to indicate which area or which object they want to inspect. And third one is that we want to really build this prototype and test that in using some experiment. So for the first task, it has 2 steps. It starts with a GPS-based course localization. What it means is that we want to use GPS system as a common coordinate system for course localization. That means the UAV can first fly to the area of interest and send the image of the scene back as a reference image along with the GPS coordinate. Then the UGV can navigate to that area given the GPS target, and then it's ready for the remote operator to provide guidance on which object they want to inspect. And the benefit of using GPS as the waypoint, because it allows both robots do not need to be in close distance. Again, it's very flexible. The UAV could navigate the whole entire construction site and find several waypoints, and then the UGV can follow that and use the reference image to locate where the operator want to inspect, and I will show that later. So as an initial test of this idea, we first develop simulation to test this coordinated localization. So what they do is that we develop a robot simulation in Gazebo and control the robot with ROS, which is the robot operating system. So here I show this video a little bit long, so I will just show part of that. So first, the UAV could travel to the site and return a reference image, as well as the GPS coordinate. Then in this video, the UGV automatically navigate to that GPS coordinate. Here we simulate a construction site. I will stop here and show some other results later. So once we use GPS for course localization, that means both robots should be in the same area. However, it is also possible that these two robots are targeting at different areas due to sensing uncertainties and different field of views. What this means is that even though they were navigating to the same GPS location, because of the field of view of their camera sensors, they may targeting at different angles and different objects. As a result, what the human want to inspect is still not within the field of view of the UGV robot. To do this, we further use vision-based flying registration to align the perspectives from both robots. So we use AI-based feature matching to register the collected images from the two platforms. And here we use CN-based architecture. It's called based method. It's called XFeed. I will not go into too technical details, but I will use this result to show what it means. So we test this outdoor. In this video, the left top corner is a reference image returned from UAV. That means this is the area that the operator want to inspect. Now, in this bigger window, a larger window, the UAV already navigate to that GPS location, and the UGV is looking for the appropriate field of view and to see, to ensure the area of interest is within its own field of view. So let's see. So the UAV will navigate around this, scan this area, and the image features are compared with those obtained from the UAV reference images. And the right top corner, there's a similarity score, which means the higher the score is, the more similar two images are. And finally, I will pause here, maybe. Finally, this is a high score in this case. Finally, the UGV or the ground robot will target at this area to wait for further guidance from the human operator. We also tested this in the simulation environment. The left corner is the reference images from the drone, and the larger window is ground robot's field of view, and you can see the similarity scores keep changing. And finally, the robot will use the field of view with the highest similarity score. After this step, now the two robots are targeting at the same area, which means the ground robot has already facing the area that the inspector want to inspect. The next step is that the operator would need to point out or identify the specific object that they want to inspect, so that the robot can automatically navigate to that object for closer inspection. So what we'll do is that we develop this gaze-based control interface. It has three modules or steps. First, the user will use a mobile eye tracker to track the eye movement of human. And in the screen, it will show the video stream from the ground robot. What it do is that it's similar like a human behavior, natural behavior. When we are interested to something, we will fix our gaze to that objective. Similar here, the operator will fix their gaze to the object that they want to inspect. Here is the yellow dot. Once it's fixed, we use AI algorithm to segment that specific object they are interested in. Here we are using segment anything model. Once it's segmented, it is mapped back to robot view, and also we use the depth sensor, which is RGBD camera, to extract the depth information of that object, so that we know the relative distance between this target object and the ground robot. With those information, the ground robot is able to navigate to the specific target. And what we are setting up is that it will move around the target and collect the data. The data will be sent back for the human operator for inspection. So we create this user interface that include network module, which will be networking with the robot and to facilitate data streaming. And it has the image segmentation module, as well as the gaze-based target acquisition module. We did some preliminary evaluation of this framework and this control interface. And we test that in our indoor space as an initial test. And we do find that we use different targets, larger target, small target, and also target with distinct appearance. So we found that a larger target with distinct appearance tend to have better results. That means we, for example, this first one, the large wood block, that means it requires fewest attempts to acquire the target and smallest error in distance. On the other hand, smaller target require, for example, this second one, the smaller target require more attempts to acquire the target using gaze and have larger error in distance. That means we still need to improve the gaze processing and the depth extraction algorithms. This video shows a demo that we did is that once the operator fixes gaze to the center object, the robot actually move around this robot through this task and keep its sensor. Here we use the camera, keep its sensor face to the target object to collect data. So after this, we have developed all the modules needed to needed for the UAV-UGV coordinate navigation inspection. Then our third task is to really develop prototype and try to test this prototype in an outdoor space. And because of the time limit and the scope limit, we only have 1 year to finish all of this work. So we choose our enclosed drone cage at UTSA as a test bed. So this is a new facility at UTSA. Because of this, we can fly the drone without much regulation constraints. So we use this as a test bed. And because of the scale of this test bed, we couldn't do the precast component, a very large precast concrete component. So we built a wood bridge as a scaled experiment. The hardware we use is that we use Husky as the ground robot, and we use a DJI drone. For the mobile eye tracker, we use pupil core glasses. And we also improved our control interface to a web-based interface, and we integrate all the functions, including set the waypoint from the drones and also collect human gaze data for target identification. So here I will play this video and explain what is going on as the video goes. So we start from a drone operator capturing the data and direct the drone to the area of interest. Here you can see the drone operator is actually could be a remote operator. She is sitting outside the drone cage. Now the drone is flying to the target area. What they do is that this drone return back the image of the scene and also return its GPS coordinate. And the drone is free to go to other area of interest after this. Then the ground robot, which is at the corner, will go to that GPS coordinates. And here we did encounter some challenges because of the low precision of the GPS sensor on the robot. This is a low-end GPS sensor, so the drone, the ground robot has some difficulty to find the actual, the correct location. And I will discuss that later. So I will skip this. We'll move to. After that, the operator is ready to indicate which object they want to inspect within the scene. They start with, of course, do some calibration and adjust the location of their mobile eye tracker. Once it's done, it can be used for multiple tasks. And they can select which data stream they want to have. Here is the video streaming from the ground robot. So we have a camera on the ground robot continuously collect the data from the site and streaming that. But here we do have some latency. And we build this wireless network on the job site, so there's some latency there. Now you can see once the I'll pause here. Once the human fix their gaze, so the column, that column is the object they want to inspect. So that red dot indicate their gaze. Then the system will segment that object to indicate that is the object they need to inspect. At the same time, the robot will use their onboard sensor to extract the distance of that object so that it can automatically navigate to that object and collect the data. So that is I would say a pilot experiment and a prototype we did for the last year. What we found is that we demonstrate the potential and feasibility of using robot system for efficient infrastructure inspection. And we also develop a gaze-based interface and prototype for UAV-UGV coordinate inspection. We found that gaze-based control could enable intuitive human-robot interaction so that we don't need very that high expertise, specific expertise to control the robot. And also imagine it can also allow human to control multiple robots at the same time, because now it requires less intervention from the human. But we do had a lot of challenges here, and the development methods need to be improved to handle dynamic and challenging environment. And the system will be tested, need to be tested in real-world construction scenarios in the future. Thank you. Sorry, I went a little bit long.
Thank you very much, Dr. Cai. Let's see if there are any questions. So we don't see any question at the moment.
And again, feel free to send me an email for future discussion. I put my email here.
Okay, thank you.
Thank you.
I just wanted to say thanks to our presenters and everyone for calling in and joining us for the May 2025 Research Highlights webinar. We will have another webinar in June. And yeah, thanks everybody for joining it. Have a great day.
Thank you.
Thank you.
Thank you.
Thanks, everybody.